The main goal of this exercise is to just give you a basic example to review how you go about with generating a Thevenin equivalent, specifically a wave that's going leftwards, to contrast that with our example in the lecture notes. And then secondarily is to once again see how the equivalence between doing a Thevenin equivalent versus the 1 plus gamma to calculate the transmission coefficient. So let's say we have this transmission line. This is our voltage at the input end. We have a ZG that's equal to 50 ohms. Let's say Z naught is 75 ohms. And then that takes us to VG, which is going to be 10 volts. Now let's just not worry about the actual entire problem, but let's just say that in the moment that we're interested in, there is a negative going wave. So there's a little negative going wave DC signal that's just peaking out here, and this V minus is going to be equal to 4 volts. So the question is, as it exits, what does the generator see? So what's V in and what's I in? So let's start by using the Thevenin equivalent approach. Now when we do that, we can draw the Thevenin equivalent as, remember, the formula is we draw a generator with the equivalent voltage that's double what the exiting wavefront is, so 2V minus, which is equal to 8 volts. And then that has a source impedance of Z naught, which is our 75 ohms here. And that is your equivalent of what V minus will look like to the rest of the circuit at the output of the generator. So the output of the generator, there's 50 ohms here. And then you have your VG, which is equal to 10 volts. So the question that we're asking is, what's this V in and the current I in? Or actually, I in is defined this way. So V in and I in, let me just iterate or emphasize that the definition of I in, given that it's input positive, is rightward, just like all the other currents that we have, or the positive Z to be precise. So now we just have to solve this circuit. So you have 10 volts, 8 volts. So the total current would just be the potential drop across here divided by the total resistance. So I in will be VG minus 2V negative. So that's the voltage drop divided by the resistors in between that it crosses, which is 20 plus 75. So that gives you 10 minus 8 over 125, which is going to be 0.016 amps. And then similarly, V in is going to be, you have your 10 volts over here, and you know the current, so you just have to subtract out the voltage drop across this 50 ohm resistor. So that's going to be 10 volts minus 0.016A, or I've been leaving out the units, so I'll just keep it that way, times this resistor, right, times 50 ohms. So times 50 ohms, and that's going to come out to be 9.2 volts. So this is what the voltage and the current actually are if you measure it here in response to this negative wave coming in. So the other way to look at it is the transmission coefficient. So let's just take a look and see how you get the same result using this. So in this case, V in is going to be equal to the transmission coefficient times this negative going wave. So 1 plus gamma of V minus. And the other subtle thing to remember is you have this negative wave going in, but you also have that initial positive wave, right? So if we go back to the bounce diagram, remember you had a wave going out and a wave coming in. This voltage here is actually not just B, but it's actually A plus B, right? When you're actually calculating what the voltage or the elevation is at this point. So you also have to add the original voltage that was going in when the voltage generator turned on. So this we'll just call V in from the generator. I'll just be more specific at t equals 0 plus, which I'll just say aka V in G. So this V in G is going to be the voltage divider between ZG and Z naught. So it's going to be VG times Z naught over ZG plus Z naught, which is going to be 10 times 75 over 50 plus 75. So that's going to be that value there. So calculate that, plug it in, and then gamma is going to be 50 new minus old, new plus old. So 50 minus 75 over 50 plus 75. And then this V minus is the 4 volts that we're given. So if you plug in this result in here, and then this value in for gamma, and set V minus equal to 4 volts, throw all that in together, you will also get that V in is equal to 9.2 volts. So they should end up being the same. So in general, you can use whichever makes the most sense to you. I would say that in many cases the Thevenin equivalent can be a little bit less confusing because you don't have to worry about things like the accumulation of the input wave as well as the reflective wave. It's in some ways it's fewer things to worry about and remember to keep track of.